This is basically about how the data is stored in RMG, but also how we get property prediction on the fly from those. These slides were mainly from Matt Johnson, adapted for 2025. Okay, so for reacting systems, we typically care about both the forward rate and the reverse rate. Um, and from thermodynamics, we can get the delta G of reaction and relate that to an equilibrium coefficient that we can relate to the forward and backwards rates. Um, from there, it's convenient to calculate the reverse rate as a function of the forward rate and the Gibbs free energies because of a few reasons. One, thermodynamic properties are easier to estimate than rates. Two, there's cancellation of errors. Three, there's often more reactions than species, so this allows us to determine a smaller number of properties. And four, thermodynamic consistency is often more important than getting the individual rates correct. So this implies that for most applications, we're going to care about two problems. One is estimating the delta G of reaction, and two is estimating the rate coefficients for the forward reactions. Um, uh, just to deconstruct this further, the delta G of reaction can be deconstructed to the enthalpy of reaction and the entropy of reaction, which can further be deconstructed as the individual enthalpies and entropies of the products and reactants. Um, Assuming ideal gas, you can get those from the enthalpies at 298 plus the integral to that temperature of desired temperature of the system with the heat capacities for both the enthalpies and the entropies. So therefore, we can get the free energies of reaction as a function of enthalpies at 298, and entropies at 298, and heat capacities for all the reactants and products. So how do we actually get those? Um, the best way, which was mentioned previously, is in experiments. And the next best way is to do quantum chemistry calculations. And these are things you might see in user libraries, which include specific values for specific species and reactions. But during an RMG run, there's often many more species and reactions that are unknown that we don't have data for, so we need a way to estimate them quickly. And so the way that we do that is through group additivity in families. And so this first part of this talk will actually talk about the parameter estimation, and then it will talk about the data. So first, let's talk about the parameter estimation. Um, One of the ideas is that to do this, is this most simplest idea is that thermochemical properties are highly linear, where you can define an enthalpy approximately in terms of bond dissociation enthalpies and individual enthalpies of the atoms. One approach we use builds on that. It's called by using what's called the group additivity. And so in this example here, you have propane with two CH3 groups and a middle CH2 group. And so you can get basically those two carbons that have CH3s on them, one carbon that has a CH2, and then there's the 6 hydrogens attached to each of those CH3 groups, and then the two hydrogens attached to CH2, and basically sum up the enthalpies from all of those individual components. Just in general, those values, this is what it looks like in theory, but in principle, the values for the hydrogens are linearly dependent on the values for the carbons. So in general, the hydrogens won't have any values associated with them. Um, okay, so how do we actually determine those individual contributions? We do that through a thermo tree in the database by descending a thermo tree to the most specific node. In the database, each node either has data, a reference to another node, or none. If it's none, it will reference up to the most general node up the tree. And these values are either from literature that we then place into their database or derived from other simple molecules. Um, for radicals, we use a similar tree of hydrogen bond increment corrections, which estimate the energy from removing a hydrogen atom from the molecule. And they're based on semi-empirical calculations, which is why group additivity usually works better for stable species rather than radical species. Okay, so this is kind of all abstract, but here's what it looks like in the RMG database. Um, on the left, I'm showing the thermo associated with one of the nodes of the tree. CJ2 singlet FC. So you can see the index. So you can see that this is all under an entry. This has a associative index, a label describing what it is, a group with the adjacency list showing, and you can note there's this asterisk here that denotes what atom this corresponds to. Um, then it has thermo associated with it, with heat capacity, enthalpy, and entropy data. Um, and then on the right, you can see that in the database, we also have a tree that we define. And this is basically um, kind of like Markdown formatted, not exactly, but it's it's separated by these tabs with going downwards down the tree. So L1 here is the root node, and then you have the children of that node at each corresponding tab. So this thermo tree is in RMG database input thermo groups group.py, and it has like many lines of these sorts of things. Like you can see here, the line numbers go into 60,000, so it's quite big. Um, but that's mainly how we do thermo groups. Um, for gas phase species. We also have values for adsorbates and catalysts. For some adsorbates, I'm not an expert on this, and I think we'll discuss more about this later tomorrow. But basically, we have ways of um, adding an absorption term, and for species, I think it's mostly relative to the platinum 111 surface. But then you can calculate different binding energies for different surfaces in some way. We'll describe more tomorrow how this works. Um, but yeah, there's some sort of scaling to any other metals of interest through relative to the platinum adsorbate. Uh, we also mentioned earlier that there's like an ML method for thermo. We don't, so, the latest version of RMG doesn't support that currently. But in the previous versions, it's recommended for polycyclic species. For most cases, though, group additivity is usually the way to go. Okay, so that's basically thermo estimation. The next thing that we care about often is kinetic rate coefficient estimation. Similar to the thermo, the best values are from experiments. Um, the next best way is to do quantum chemistry calculations, but as anyone who's worked with this before knows, these can be really quite tricky, especially compared to thermo, because you have to compute the transition state, and finding those is not always trivial, and so on. Um, and when we're thinking about how to extend this to fast prediction, there's some things that make it more difficult than thermo. For example, the relationship between the structures to the rate coefficients is really nonlinear, and so you can't kind of do this group additivity approach very well. There's a lot more special cases also where just having a slight difference in your structure can lead to a huge change in rate. Um, and you usually want to get more of an exact answer if possible, because these will determine, like ultimately at the end of the day, you want to determine the time evolution of your system, as opposed to thermo, where it's more where consistencies may be more important. Okay, so given all of that, how we do things is to rate trees, which is we structure our rate information inside these isomorphic trees and use distance between nodes within the trees to determine what kinetic parameters should be best for what reactions that are provided. So here's an example. A rate family is a recipe associated with a certain set of trees. So you can see here is the rate family R addition multiple bond. Um, you can see there's two trees here. Each tree independently describes a section of the reactant's molecular structure. In this case, it's a bimolecular reaction. So there's one tree that corresponds to the R double bond R, and then there's another tree for the R radical. Um, each node structure in the tree is subgraph isomorphic to its parent structure, so that basically um, it's like it's a smaller set that's contained by the parent. Um, um, so some of the information that we include in the rate tree, we have rate rules, which are fixed in the rate tree. We have training reactions, um, through which we design down the tree to find the most specific pair. And then we have averaging rate rules, which is basically, actually, let me rewind a little bit. Um, each of the when we have a reaction, we descend down the tree and basically try to fill it in as much as we can with existing data from basically like matching coordinates of each of these nodes. After we've done as much as we can, we then do averaging, where we basically take the rate of um, of a species and its children and average it with uh, sorry, like it's kind of like if you're comparing this like C double bond R and H radical, for example, and this had children, you'd take the rate of this and the children of this and multiply it with the children of the C double bond R and the rate of this, just to give average rate rules, especially if none are available. Um, Once the tree is full doing it that way, we estimate the kinetics by descending down the given trees. If there's no information at each of those like coordinates, the closest information that we can get is used from like from up the tree. Um, basically, if there's no kinetic information possible from a certain node coordinate pair, um, you estimate it by what's closest to it, just going up the tree. Bimolecular trees usually have two different trees, one for each reactant, as we showed previously. Unimolecular trees usually have three trees, one for each N group and one for the backbone. Um, for instance, you might like why that might be important is like the backbone might uh, create a different membered ring of the transition state, which can strongly affect the kinetics, for example. So that backbone is also important. So now we'll show an example of the rate tree. Let me see. Kinetics families intra-migration. Okay. So this is an example of, yes, I will do that. So this is this is in the RMG database, which comes with your install. It'll be an input kinetics families. In this case, I'm looking at the intra-H migration. And here, the important thing is that we're defining a recipe for what each of the reactions in this family looks like. So basically here, every node in this um, tree, every reaction is going to have bond breaking at the 2 atom and then a bond with the 3 atom and then forming between the 1 and the 3 and so on. And you can define what like the radicals are gained and so on. And these basically define the nodes that are in the tree. If you go to the bottom, let's see if I can find it here. You can see where the tree structure is defined. So here we have like L1, and then the topmost node is the RNH, and then progressively you get more specific nodes. Since this is a unimolecular family, there's 3 different trees. So this is YRAD out and XH out. Another set of information that's in here is the rules. And um, here's where the kinetic information is stored. So here we have basically 3 of the nodes from the trees, and we've defined kinetics for that coordinate of those reactants, basically.
Yeah, we pass this down to you.
Maybe a stupid one, but if I'm only a user, do you also need to define this tree, or is the tree defined, or is the tree only important for developers and the users simply say, I want to investigate A plus B to C, and the tree is automatically defined?
That's a great question. So these are all predefined families that other developers have made. So the user, like in general, you won't need to worry about these really, in terms of like defining the tree or anything like that. Where it might come into play is if you want to add your own kinetic data. And a later session will discuss that more. We have some scripts that help automate parts of that. Yes. See another question?
So I guess one, my understanding here is that you're descending on the trees, so in the hope that at some point you'll encounter cases where there are lab or existing high level measurements, and then from which you can go back up and estimate the rates. Is that the basic idea here?
Yeah, so you're when you have your reaction, it'll match down to the most specific node as possible in the tree that is isomorphic to your reactants. Those are either populated from existing data or consist of like averages from other nodes or estimates from other based on like other nodes. Um, so they're not always super accurate. But the metadata that's provided in the nodes often tells you like what those values came from and how much you can trust it. I'm not sure if I can maybe find some examples here. This one, for example, is for these like coordinates of nodes, and these are from like QM calculations at the B3 lip level. Trying to see if I can find. I guess these are mostly from experimental data. But yeah, you're right. Like it's descending the tree in that to find the most specific matching subgraph isomorph.
Okay. And I guess a general question, like to what extent this methodology has been sort of validated? like have you tried to force to do the tree thing for a reaction that we already know very well what the rate will be, and then, to see whether the prediction actually matches with the knowledge?
Yeah, so a lot of the benchmarking was done like previously, like before I joined the group. So I actually don't know exactly what benchmarks were done, but there definitely have been some. Richard, do you know exactly more details?
Thanks. We've invented many alternatives over the decades. None of them are better than this.
Yeah.
Except perhaps Matt Johnson's automated tree generation, which he'll talk more about, I'm sure, the SIDT. He basically, these trees were handcrafted by a chemist, most often Bill, or his students, but with Bill watching over the shoulder. And it turns out that that really helps, that he knows that having a double bond is more important than being next to an O, or vice versa, right? If the chemist decides the branches in the tree, you can then often benefit from that. It's kind of like machine learning, but you're helping it learn with its knowledge. The new automated system, if you have enough data, can make those choices automatically. It will decide, oh, I can make my overall predictions more accurate if I split this branch point in the tree based on my neighboring atom, or based on the strength of the bond, or based on something else. It makes those choices based on the data. And it turns out that this is fairly data efficient as a machine learning tool. I mean, neural networks and so on are great, but need orders of magnitude more data than these trees structures. And the hand-built trees need even less data because they had a chemist involved. But I think the automated ones show some benefits. And so there's kind of half our families now have been converted into these automated trees, and half of them are still hand-constructed trees. But it's a very data efficient way to do machine learning, and it also shows where things came from. So it's kind of, you can look into the book, into where it came from, which is another benefit.
Yeah, thanks, Richard. Another comment on that is we used to support group additivity for kinetics, but that turned out to work really poorly. Oh yeah, the slide actually says. So it's now deprecated in RMG as of I think last year. You might see it in previous training materials, but yeah, we don't support it anymore because it's much worse than the trees. As Richard said, we have automatic tree generation now. I think it's implemented for a lot of the kinetic families, but not all of them. And in many cases, it can reduce the uncertainties a lot. We'll show later how you can generate these trees automatically. And that automatic algorithm is shown here. Basically, you start with a tree, and then as long as there's training data, create sets of possible extension nodes, and then see which extension like has the minimum error, for example, or the minimum. There's some sort of loss function I forgot on that basis, and repeat iteratively. Okay, so those are ways that we estimate thermo and kinetics. Now, from the data side of things, it turns out it's really quite simple. It's just a mapping of a structure's thermo to what's in the database. So like if you know the thermo for ethane, you can just retrieve it from the database immediately. So that's quite simple. For reactions, these it's quite similar in that it'll match the exact duplicate reactions produced by RMG, but it won't replace equivalent reaction pathways. For example, if you have A goes to C, it won't replace A goes to B and then what goes to C. But in general, these are both like sorts of like exact matches to either your reactant or your reaction. So we'll take a quick look at a couple of those examples. This is CVS QB3 1D hindered rotor. This is in input thermo libraries, CVS QB3 1DHR. As you can see, these are basically QM calculations. And here we include the adjacency list for the structure for the molecule, and then we list out its. I'll zoom in a little bit. Its associated thermodata. So here we have heat capacity, enthalpy, and entropy, and so on. So this is pretty straightforward for thermo. This is a kinetics library, and you can see here it looks a little different. For one, the label doesn't have adjacency lists anymore, it just has labels. And we define the kinetics. Let me see if I can wrap. You can define the kinetics here. Here we just described an Arrhenius rate, for example. But you might wonder, like, how does RMG know to go from H and O2 to the specific molecular structures? You have to, in each kinetics library, separately define a dictionary. And in those dictionaries, that's where you list out the adjacency list for a certain structure. I guess the reason we did that was just to prevent the reactions from being really long and bulky to read. But that's why it looks different from the thermo. Okay, so this is the last slide. Once you have predictions or library data, you might want to use some of these rules of thumb to figure. Sorry, it's the rules of thumb that we discussed previously, and some of the thoughts here. When you're looking at libraries, you might want to consider what kind of sources were used, or some of them fitted or guessed, and especially if you're looking between like experimental and quantum chemical data, for example, and the level of theory. For thermo, you want to know how specific the nodes are used to estimate certain atoms, and if there's data at that node, or if there's reference to a certain nodes up throughout the tree, and so you're really looking at like an estimate of an average. For traditional rate trees for kinetics, same thing. You want to know. You basically want to like if your rates are estimated or not. And one of the cool things about the automatic generated trees is that they inherently have estimates of the uncertainty, so you can use those explicitly as like proxies for how much you trust your node coordinate like kinetics. That's all we have for this slide deck. Does anyone have any further questions? Andy does.
Thanks. For the trees doing the kinetics, does it do that individually for the Arrhenius parameters, the activation energy, the pre-exponential factor, or is it doing it once for a given set of conditions? Does that make sense?
That's a good question. So you're asking if it's like the kinetic parameters that are being like, for example, averaged and propagated, or if it's,
Right.
Yeah. Do you know the answer to this, Richard?
The Flowers Mazel trees, they take the training data are Arrhenius parameters, and they I think they weight them. So they take a bunch of different temperatures for each of those, and they each have a different weight, and then they fit they fit a Blauer's mazel, which is similar to the Arrhenius kinetics for anyone who isn't aware, but it adds an extra the enthalpy, I believe, changes, or the activation barrier scales or changes with the heat of reaction. And so what you end up with then is the all the parameters for that are based on that set of training data that match that particular node or description of the reaction end up being a single set of parameters. So you basically start with maybe like you've got 4 training reactions, you've got 4 sets of parameters, and then you're fitting a node that'll have a single set of parameters. Does that answer the question?
I think so. So it'll do that once for a reaction. It doesn't have to do it for different temperatures if you're doing like range of temperatures. But thanks.
Yeah, we have a question on Zoom. Somebody raised their hand.
Hello.
Hello, yes, we can
Hello.
hear you.
Yeah, thank you for the explanation in the workshop program you've been following. So I need to clarify some things regarding the thermal and the kinetics. So this has to do with the heterogeneous system, like where you have the catalyst in the system. So this thermodynamics, the thermal database or the library that is being specified here. So does it take into cognizance systems that are not like pure metals, surfaces that are not pure metal?
Not yet.
And and the other one regarding the kinetics, must one use the tree, or is there a way to do without using the tree? Like if you have some data from quantum chemistry that you want to employ into it.
If you have your own data, you put that in a library. So if you know the rate of a certain reaction, put that in a library. Put the library in your input bar. It will use that first, and it won't estimate it from the tree. It will use it.
Okay. So, but what about the thermodynamics regarding the surfaces that are not carried out on pure metals? Maybe either alloy or maybe metallic oxide.
If you know the thermochemistry, again, you can put it in a library. You could even put it in your own copy of the tree that's not the platinum tree. But at the moment, the only thing it can predict is pure metals. And in fact, the only thing it can predict well, I'd say, is platinum 111. And then from there, you can scale it to other metals using linear scaling relations. So we scale it to all sorts of hypothetical alloys in our workflows often by making up binding energies. It's kind of useful to have a few parameters that you can scale it to. But then they really are estimates.
Okay, I get your point. Like, if you have a different surface, so instead of totally just changing the platinum to N, so you can just rescale the binding energies that are provided in the catalyst model to do that. That's like you kind of make some relative changes.
Yes, and that's kind of automated, so it will apply linear scaling relation. We have a catalysis session tomorrow, I think, which will explain more about how that's done.